Good morning, good afternoon, good evening to everyone. My name is Jan Dousa, and it is my pleasure today to present my heard topic, GNSS real-time troposphere monitoring. Let me start the talk with a brief introduction with background information. I will then focus on real-time processing strategy developments and demonstrations. Finally, I will describe the state-of-the-art operations and validations. The concept of GNSS methodology has been introduced by Rosa Pacione. It is turning a noise in geodetic applications into well-established parameters useful in meteorological applications. GNSS signal is delayed and banded by the atmosphere. Both effects are attributed to atmospheric constituents commonly parameterized in numerical weather model (NWM). The interesting one is the water vapor, or its integral value in profile to which GNSS-based signal delays can be converted. The bottom figure shows the integrated water vapor parameters stemming from two GNSS solutions as well as derived from numeric weather model. Obviously, precise GNSS is able to capture high temporal changes in water vapor distribution and not observed in numeric weather model. The concept transformed GNSS receiver from a positioning tool to an atmospheric sensor. The standard observation model for the troposphere introduces zenith tropospheric delay, ZTD, parameter which consists of hydrostatic and wet contributions. Both are projected into the line of sight by the so-called mapping functions. An extended model adds horizontal linear gradients along with ZTDs. However, for gradients, wet and hydrostatic contributions are combined. High temporal variations or high spatial anisotropy effects could also be observed in carrier phase residuals along with other unmodeled errors. Slant path delays could be then retrieved from the post-hit residuals and estimated parameters, hence bringing advanced information for 3D water vapor reconstruction or monitoring extreme weather. Anyway, residuals should be clean of systematic error for such as a multipath effects. All information derived from GNSS analysis are of interest for nowcasting and several weather monitoring applications. For completeness, I would like to mention also hydrometers, the effects due to the presence of liquid water, ice, snow, cloudbursts in the atmosphere. Although the effect is very small, it is closely related to several weather conditions, thus raising a strong interest for nowcasting applications. Two figures now shows spatial and temporal occurrences of this effect caused by the liquid water during heavy precipitation in Central Europe. The difference between weather forecasting and nowcasting is explained to better understand requirements on GNSS product. Forecasting is based on numeric weather predictions, employing models of physical atmospheric parameters. Its typical range is from hours to days. On the other hand, nowcasting maps the current weather by applying simple visualization and extrapolation methods, underlying only optical flows. Typical range is between 0 and 6 hours. While the requirements on the GNSS ZTD accuracy remains the same, the difference lie in latency and temporal and spatial resolutions. A brief overview about the development of GNSS methodology includes significant international projects. Since 2005, the EGWAP coordinates operational near-time solutions. Gray color indicates mandatory prerequisite for GNSS precise analysis, data flow, precise products, models, and services. Blue color represents the demonstration and operational analysis. Brown boxes introduces operational utilization in numeric weather model analysis. Red color then represents real-time related production. The box frame finally represents target developments of continuous GNSS tropospheric multiparameters products delivered with an unprecedented time resolution and almost no latency. Traditional real-time batch solution relies on the least square estimator using deterministic parameterization and double difference observations. This strategy still dominates among EGWAP services. Its main advantage lies in eliminating satellite clocks and biases. Real-time PPP was enabled by the IGS real-time service, streaming state space corrections for satellite orbits, onboard clocks, and biases. The PPP supports absolute troposphere estimates, however, requires accurate models and their consistency with the correction service provider. The PPP support implicitly the processing in a global scale as well as at remote stations. It is particularly popular for an efficient handling of real-time and multi-GNSS data, for high temporal parameter resolution, for simple retrievals of advanced tropospheric parameters. The PPP driven by real-time inputs and combined forward-backward filters was used for developing also all-in-one strategy adaptable for simultaneous real-time and real-time production. Real-time versus near-real-time processing is trade-off between the accuracy and the latency. Standard least square solution uses deterministic models, like a piecewise linear piecewise constant, which may result in discontinuities of estimated parameters at boundaries of each batch solution. The real-time PPP is then driven by a continuous forward filter for stochastic estimates of tropospheric parameters. The PPP is capable of providing simultaneously near-real-time solution in blue circles if backward smoothing is additionally applied. The main deficiency of real-time filtering is shown on this plot. A fast decrease in ZTD 7 cm per 4 hours demonstrates how is the forward filter capable to reflect such a fast change. A priori sigma for the random walk noise is commonly introduced empirically. In this way, it can easily be underestimated or overestimated. The former causes a slow adaptation of ZTD to last observations. The latter may cause generally decreased accuracy of ZTD by overweighting recent observations over past ZTD estimates. An optimal noise should consider actual troposphere dynamics. A smooth solution indicates a potential 20% improvement in accuracy of estimated ZTD, however, on the cost of increased product latency. The smoothing effect increases with the length of the period. In other words, the accuracy increases thanks to the contributions from recent observations to the older ZTD estimates. The scheme shows inputs/outputs for real-time PPP. Station metadata and models are introduced from files. Also, tropospheric outputs are regularly saved in files in the troposyntax format. Observation data, navigation data, and precise corrections are continuously streamed over Internet using the N-trip protocol. The N-trip caster enables flexible dissemination of any data streams. Real-time PPP engine collects the input data with parallel N-trip clients connected to the N-trip caster. The software needs intensive threading for simultaneous input data and output data handling and station processing. Observation data and global navigation data are collected from individual streams. Orbit and clock corrections are made available from various data sources. For example, combined solutions from the IGS real-time service or individual correction services providers. Recently, a unique source has been provided by Galileo High Accuracy Service via signal in space, that's directly from satellites, but also via internet dissemination. Equality of SSR corrections is critical for real-time PPP solution. A snapshot of evaluation of different correction sources includes 5 years of IGS real-time service and 1 year for Galileo High Accuracy Service. Typical accuracy performance 1 sigma is 5 cm in 3D satellite position and 5 to 10 cm for onboard clock corrections transformed to the units of length. The availability and robustness is also important, along with the continuity and support of individual satellite constellations. Nowadays, IGS real-time service supports all global GNSS constellations, while Galileo High Accuracy Service only Galileo and GPS systems, with a typical performance of 5 to 10 cm in 3D satellite positions and 10 to 20 cm for clock corrections. Such a lower accuracy, compared to the IGS real-time service, is attributed to less global stations used for the product generation. Real-time tropo monitoring was triggered by the IGS real-time service in 2013. Several studies were initially performed within the cost for SWEC action, for example, the impact of corrections extrapolation, visible in top left figure, the impact of simultaneously estimating ZTDs, and receiver position using statics or pseudo-kinematic processing mode, left bottom. Both these processing modes confirmed satisfactory results for supporting an estimation of real-time ZTDs from moving platforms. Besides, 3 software packages and 2 extra strategies were assessed for revealing a readiness for continuous real-time ZTD estimates. In April 2013, initial ZTD instabilities were improved by completing all critical models in the software left side. Routine solutions started by evaluating 2 IGS correction sources, IGS-01, IGS-02, and a CNES individual correction source. Mean ZTD standard deviation achieved a sub-centimeter level quality, however, large systematic errors remained, even though they were steadily reducing. A consistency in models between client and service are critical in PPP analysis. Finally, similar results were achieved for European as well as global stations, confirming an implicit support for a global production. Station statistics were computed with respect to the UREF combined and IGS final reference product. ZTD biases are displayed on the left-hand side, standard deviations on the right-hand side. Precision is characterized by 10 mm, only a bit worse for global stations. High variability among stations is visible for systematic errors, still dominating the initial production, and attributed to the lack of knowledge about model consistencies. A better quality of corrections from CNES compared to IGS suggests an issue with full consistency of inputs within the combination, since theoretically the combination should bring the most reliable and accurate product. The GNSS for SWEC Action also organized real-time demonstration campaign for motivating various groups to contribute to development. Altogether, 32 European and global stations were selected, although not everyone could process all stations. Some solutions included the second constellation, GLONASS, or horizontal gradients. Assessment proved that the quality is already satisfactory for nowcasting applications after reducing systematic errors to an acceptable level with respect to the precision. GNSS for SWEC benchmark campaign, designed specifically for severe weather monitoring, was additionally used for simulating real-time tropospheric estimates. The campaign was organized in Central Europe during May-June 2013, when repetitive heavy precipitation caused several floods in the area. Simulation helped assessing the impact of real-time strategy and products compared to the post-processing ones. GNAT software was ready for both simulated real-time and post-processing solutions using PPP and Kalman filters and smoother. 2 reference solutions were derived using 2 scientific software, Bernice and EPOS, both applying least square batch adjustment with purely deterministic models. Network versus PPP processing mode remained as a difference. The study confirmed a very good agreement among all the solutions, indicating 10 to 25% of degradations when using real-time corrections instead of precise products. Unfortunately, a common positive bias of 2 mm in ZTD was not satisfactorily explained. Benchmark campaign included several weather fronts with heavy precipitations. 3 plots showed GNSS horizontal gradients estimated by different GNSS software and strategies, including parameterization models and time resolution. We can clearly observe an excellent agreement among all the solutions variants during this very specific event. GNSS gradients reached magnitude up to 7 mm, pointing towards increased water vapor. The integrated water vapor content is visible from 2 left maps, one using numeric weather model Aladdin CZ and another using GNSS PPP. Excellent agreement is obvious and both solutions involved completely independent datasets. Weather front brought heavy precipitation in northwest to southeast direction. Estimated gradients nicely captured the situation in terms of both magnitudes and directions. It is obvious that GNSS-ZTD gradients can play a significant role in nowcasting. It is, however, more difficult to say it about the small gradients below 1 mm, since the uncertainty in their real-time estimates are high, particularly due to the capacity to absorb any unmitigated errors. Last but not least, benchmark could demonstrate the role of posted carrier phase residuals obtained from PPP. By comparing results at two collocated stations during 2 consecutive days with different weather conditions, we can notice a large scatter at both stations on June 20. This proved that the residuals could be suitable at least for indicating extraordinary temporal or spatial water vapor variations. Ionosphere-free linear combination of original observation is traditionally used for eliminating the first-order ionosphere effect. PPP raw observation model was introduced in 2011 for exploiting original observations at the dual, triple, and quadruple frequencies. The model keeps original noise of signals when avoiding its amplification due to the ionosphere-free linear combination. Slant ionosphere path delays plot at ground pierce points in figure represents a useful side product. Disadvantages can be seen in a higher complexity, more parameters to estimate, and needs of code and interfrequency biases. PPP raw model was assessed in parallel real-time operation along with the standard PPP model. 3 years of comparisons demonstrate a very good agreement, if not considering the period prior June 2022. Initial degradation in both solutions were caused by a mistake, not correctly introducing satellite PCO-PCV models. The quality was assessed by monthly mean ZTD RMS over all stations with a reference given by UREF combined product. Additionally, RMS were calculated from ZTD differences at collocated stations. GNSS low-cost receivers with dual frequency carrier phase observations became available on market in 2019. Two such receivers, GOP-B and GOP-C, were connected to different antennas nearby the geodetic reference station, GOP-E. Real-time ZTDs and gradients were then estimated simultaneously employing PPP ionosphere-free and raw models using the same software and precise corrections. GOP-B shows very good agreement with respect to the reference source station. However, GOP-C resulted in values degraded by a factor of 2 or even more. This is attributed to the simple patch antenna at GOP-C, revealing its strong impact on the results. Generally, GOP-B instrumentation suggests feasible and affordable solution for densification of GNSS atmospheric sensing in real time. Additionally, snapshot of ZTD time series from GOP-B is compared to collocated GOP-E and GOP-6 reference stations. Closely collocated station proved to be an excellent setup for advanced validation of any GNSS tropospheric parameter. 10 dual stations were selected in Europe for assessing operational products. Table summarizes the station list, including instrumentation, horizontal and vertical distances. Statistics on left side are computed station-wise using ZTD differences from real-time solutions compared to reference one. Contrary, statistics on the right-hand side consider ZTD differences between dual stations. A significant reduction over 50% in all statistics demonstrates a strong correlation between collocated stations. This is caused by common errors from real-time products and possibly by real-time modeling. Achievable accuracy seems to be limited primarily by the quality of the real-time corrections and employed ZTD parameterization. Evaluation of different correction sources showed that IGS-01 epoch-wise combination provide the best performance. A similar precision was achieved also with the CNES product, however, with higher positive biases, indicating some problem with consistency of processing models. Yearly time series of ZTD and gradient differences were calculated between GOPE and GOP6 and showing typical fluctuation in quality and of estimated tropospheric parameters. Variations are slightly higher during summer months, which corresponds to theoretical expectation. Strong similarities can be easily observed. Yearly time series of ZTD and gradients differences now from dual stations show a dramatic reduction of original discrepancies. This is an evidence of presence of strong correlations at dual stations attributed to a common impact of using precise corrections, which is particularly true for estimated gradients, extra sensitive to absorption of any mismodeling errors. The real-time estimation of gradients still remains challenging for nowcasting applications. Several operational real-time solutions are running in different spatial domains, European, global, and regional. Networks are split to clusters and for easy validations include some collocated stations. Over 350 stations are operationally analyzed with ZTDs and horizontal gradients stored for every 5 minutes in sub-hourly output troposynix files. SSR corrections from Galileo High Accuracy Service were compared with those from IGS and CNES. 3 solutions were assessed for HAS: Galileo only, GPS only, and GPS and Galileo combined. In addition, GPS solution from IGS and combined GPS, Galileo, and GLONASS from CNES were included. Monthly statistics were computed using ZTD differences with respect to the UREF reference product, and additionally in between collocated stations. The CNES multi-GNSS solution performed the best, achieving ZTD accuracy of 4 to 6 mm for individual stations. The GPS solution from IGS performed as the second best. The Galileo HAS provides less accurate clock corrections for GPS compared to Galileo, which may explain a worse standalone GPS product, characterized with ZTD accuracy of 9 to 10 mm. The standalone Galileo solution from HAS is more accurate compared to the GPS and Galileo solution. Similar results were achieved by inter-comparisons at dual stations, with RMS improved by a factor of 2 or 3 when compared to individual stations. Galileo High Accuracy Service is also operationally used now in global real-time ZTD estimates. Table shows the evaluation of ZTDs reaching RMS below 10 mm. The exceptions are Kourou stations and stations from the Pacific and East Asia area, marked in gray, which are located outside Galileo High Accuracy Service supported area. Figures eventually shows sample time series of ZTDs and ZTD differences at the Yellowstone station. At the end, the operational web monitoring portal is introduced. It serves for fast visualization of real-time tropospheric estimates, including interstation and inter-product comparisons. The portal is publicly available and, for practical reasons, it is updated only every 1 hour. It enables interactive browsing of different networks, regional, European, and global, with colors indicating different processing clusters. The second video focuses on time evolution of ZTDs estimated from 4 GNSS permanent stations in Sweden and Finland. ZTDs at all stations follows the pattern of fast decrease in ZTD but delayed in time. The last video shows the collocated station at Onsala Space Observatory displaying a consistent 2 production lines at Onsala Station when using CNES and Galileo High Accuracy Service corrections. Then the similar production lines, and results are showed for the Onsala 1 stations. Thank you for your attention.